16 of Qubit by Qubit. Let me actually share my screen with, there we are. Okay. With the slides for this week, we are still in I don't have a computer mode, so things are a little bit more difficult than usual, but hopefully not too bad. Yeah, this week I do have a computer because I'm at work, so that's a 1+. And we will be doing now, instead of the quantum experience where we have drag and drop gates, this week we're instead going to be using Jupyter notebooks to program the quantum computer in code, kind of like how you expect to program a computer. So yeah, I'd also like to, before we get started, give a note that we have a diversity in quantum computing conference happening this Saturday. It's free and you can register now for it. It's through Qubit by Qubit, and they're putting on having lots of great speakers, lots of panels on how people got involved in quantum and their experience in it. So if you're interested in that, then definitely register at this link. I believe it's also been sent out through Canvas, so I'm sure it will be great. There's been a lot of great work put into it, so definitely attend if you have the time. Yeah, okay. So today the program is we obviously already had some announcements. We're going to go through the attendance quiz and the Zoom feedback as usual. And as usual, the attendance quiz passcode. I don't have my pencil. Is in the bottom. And now it won't write. Okay. Down here. No. Yes. Maybe. No. Okay. My pencil's not writing, but it's in the bottom right corner as usual. I will annotate as soon as my pencil decides to connect. We also, oh, now it's time to connect. What? Why? Okay. Okay. Can I? I'm sorry that I'm having just constant struggles. I swear it's only due to not having a computer. I promise. Yeah, it is writing now. And also as a reminder, we've gotten a lot of questions recently. Please remember to check Canvas for the announcements each week. All the course reminders and all the slides from lectures will be, and labs will be posted there. And all the instructions for quantum experience are there. We have sent out a Jupyter notebook that you guys can run on your quantum experience for today. And I'll be going through the same one so you can follow along and run the code. It's all filled out for you, unlike the homework for this week, which is not filled out. And so if you are ever unsure about syntax, if you have a reference version. And this will also have announcements for events like the Diversity in Quantum Computing conference we're having this weekend. Okay, so that this week's Canvas attendance quiz, I'll give you guys a little bit of time to do, just because there's 4 questions that you need to answer about your quantum states, how to measure them, and what different characteristics they have. Oh, one of my lab mates has popped in, so I'm going to put my mask. She's gonna be out. Yeah. So this quiz will not be graded, so just put whatever you feel is best for these 4, and we can go through the correct answers at the end of lab if you guys are interested. It shouldn't be too long of a lab today, so hopefully you can go through all the material and ask plenty of questions on it. Yeah. With that, I guess while we wait, if anyone has made any fun circuits in the quantum experience or have images of it, or if you want to describe it, you can put it in the chat. So I just want to give a little bit of time to go through these questions because there are more than usual. Okay, I don't know why my, sorry, since I'm in lab, like there's just like stuff happening. So I hope there's not too much background noise. We have like a bunch of pumps that pump down our refrigerators and stuff. I think you guys have actually gotten a tour of our lab specifically on behalf of Aziza before. So it's the same one. But yeah, so there aren't any fun circuits, then I'll move on, and hopefully you guys have had the chance to go through the quiz. I also have our pre-lab Zoom feedback. So just how well you understood this week's content in lecture, which this week was just an introduction of Qiskit. And we'll be doing very similar stuff in lab this week. Okay, cool. So I'll let you guys be filling that out. And while we wait, I will go through the questions that I got from last week, which, sorry if I'm like making noise. I'm trying to flatten my iPad. So the question we got a lot was, how does a CNOT gate work? And there's a few different ways that you can write out a CNOT gate. But I'm going to just do a pictorial version first, and then I'll give you the matrix version. So if you have two quantum states that are going into a CNOT, which is written like this. This whole thing is your CNOT. It's a 2-qubit gate. And where the dot is your control qubit. And this one is your target qubit. It's kind of almost self-explanatory because the plus kind of looks like a target, I guess. But this symbol just by itself, in quantum experience and in general, does just mean like a not operation. Generally, so if you just see this somewhere, that is a not or an X gate or a pi X. You'll see it called sometimes. So like we saw in the block sphere, an X gate by default, just like an X gate that you see written out, is a pi rotation around the X axis of your block sphere. And then this dot actually also exists in quantum experience, and that just is a control of some kind. So you can control one bit based on one qubit based on another qubit. I don't think you can based on a classical bit, and the operation will or will not happen. I think the equivalent version for a classical bit in the quantum experience is the if like statement, which is just like an if, and it's a classical operation that is just dependent on the state of a classical bit. So that is your CNOT arrangement, and what you have for your CNOT matrix looks like this. And your quantum state, if you have a 2-qubit state, it is a length of length 4 long. So I'm just going to write them out as like psi11, psi12, psi21, and psi22. And then you can just multiply it to get your output. So let me get a little bit bigger. Oh, cool. I have been left back to my own office. I'm unfortunately a low tier grad student, so I don't have a private office, but someday maybe I will. So if you perform this operation and you can decide to set your like qubits to different states. So if we say that we are in the, if we say psi1 is equal to the 0 state and psi2 is equal to the 0 state, then we populate this with just zeros all the way down and we'll get a 0 out. Where it gets interesting is when psi1 is equal to a 1, then what happens is the 1 is maintained. So the way that you'd represent this like result, I guess, that, oh, let me try to draw it out. That should be 0, 1, 0, 0, or no, 1, 0. Ah, 0, 1, 1, 0 for your 0 state and then your 1 state. And then you can write them, like you can multiply them through. And what ends up happening is you end up with 0, 1, 0, 1 because you flipped this state. Yeah, so that's like just a quick way of like describing how you can use the CNOT gate. You can go through this mathematics as needed whenever. And yeah, that's kind of two different representations. An easier way to think of it is if you just take it as if your control bit is 0, then nothing happens and you'll just get your same input state out. And if your control bit is 1, then you'll flip your output state. And that's all you really need to know for any of that. Cool. So now our learning objectives for Lab 16 are practicing the ability to create quantum circuits using Qiskit and using the software interface with Jupyter notebooks on quantum experience. This includes defining qubits, applying gates to qubits, and then putting out like visualizations of your qubits. And so that's if you are familiar with Python, it's actually the exact same like Python package as you may have seen before. It's based on Matplotlib, and we'll actually see when that kind of comes in. And then we're going to use all of these tools to create the same entanglement circuit that we did last week. So just as a brief review, sorry, I should really charge my pencil. The quantum circuit model we'll be using has your input states, which by default are all initialized to the 0 state. And then you can go through a sequence of gates that performs your computation, and then you'll measure in the end. In our case, we'll be measuring in the Z basis with all of the actual measurement operations we do. You can, like, as always like to specify, you can like artificially measure in a different basis by treating by using some single qubit gate on all of your qubits to rotate them into whatever base, like to rotate them into the Z basis from the Y basis, the X basis, or whatever, or the plus minus basis, whatever you want, and then measure that, and then considering that whole block as your measurement step. But this actual measurement operation is always in Z. But what it would look like if you added like another gate to measure different bases, you could add like some gate like here on every qubit. And I just put U to mean a unitary single qubit gate. Okay, cool. And I've gotten a question about the full gate, but Surya has answered it very, very well. So I'm not going to answer it. If anyone wants to know answers to things, definitely, like, if you guys know answers to questions, I think it's very helpful for learning purposes to like just like explain how things happen yourself if you do know. I think that's actually a great part of teaching, is that you tend to learn things better than you knew them before. So I definitely recommend answering any questions you know. Okay, cool. So now we're going to go code some circuits. I'm going to give like, I guess, a slides version of what you're going to do, and then I'll show you how to do it on my computer. So the first step is to log in to the quantum experience and go to the quantum lab tab, which is this like sideways parentheses. And then once you're there, you can upload this week's notebook, which you should have had uploaded on Canvas using import. And that's that. And again, the Canvas attendance code is in the bottom corner, and it's going to be gone very, very soon. So note it down if you need to know it. And I'm going to go back to my Zoom. Okay, I'm going to stop my share. So hello, I'm alive again. I'm a face. Okay, and I will share. Here we are. This is, I already have it open to quantum experience, but I can show you what it would look like. Oh, wait, not loaded. Okay, cool. This is what, if I log out, I can show you what it looks like. You're going to log in with your IBM ID here. Oh, okay, cool, I did save it. Wait, what? Okay, no, okay, I did log in. Okay. And then you go to Quantum Lab, which is the side-base parentheses, these 3 dots. And I've already imported the file, but if you need to import it, you just click import and choose the file you need. So here is the same thing that you should have on your Canvas, and give you guys a second to upload it if you're not quite there, because it is best to just run along, since you might have issues with your like importing or like running any particular part of the code. I'll give you guys a second, and I'm going to try to figure out what's happening with my Zoom. Okay, there we are. Nice. Yeah. Oh, yeah. Also, if you don't have, like, you guys may have gotten multiple Python files, like, or Python notebooks from Canvas. This is one for Lab 16, not for the problem set for this week, or the homework for this week. Cool. Yeah. So there's a lot of text on this. You don't have to read all of it. It gives a lot of detail, and which is useful as reference, but we won't be going through it like verbatim or anything. But things that are important to know is that if you hear me call this a notebook or a Jupyter notebook, anything that ends in IPy, like IPYNB, is a Jupyter notebook. And we'll be using this platform on the Quantum Experience website with Qiskit, which is actually just a package or a library within Python. So it's not its own like programming language or anything. It is just a package within Python that you can use, and it's very helpful. So let me try to resize this bit. Okay, cool. Yeah. So what the basic portion, I'm sorry, there's a bit of a lag. I can see that it's lagging a little bit. So I'll try to not go too quickly. But the basic block that we're going to be operating with in Jupyter or in these notebooks is called a cell. So each of these little sections that highlight blue are cells. And you can control the operation or the running of these cells in either the top bar with these, like, you can move your selected cells up or down. You can run a particular cell. You can like restart an entire kernel or run through the entire notebook. There's all these different options that you have, but you can also run it with keyboard shortcuts on like your keyboard. So how I normally run cells is using Control plus Enter, and that will run your cell and actually go down to the next cell, so you can then run that one easily. You can also manipulate the cells that you have with this. And if you want to make a cell, so you can, like, I create one. Oh, why am I hitting? I'm hitting on my wrong keyboard. It's like, why isn't it responding? I was on my iPad's keyboard. Okay. There we are. You can create a cell with A to do above or B to do below. And if you hit D twice, once you're escaped, it'll delete the cell. You have to make sure it is blue on the side to use all these shortcuts. If you don't have it blue on the side, then it will just type. And if you want to create like a text cell, like you see all these cells here are like markdown actually, so you can click twice and see it in this form, like this ugly, not formatted form, which you can then also run. You can change the type of cell you have with the cell dropdown. So that's how we did that. It's nothing like super special. Yeah, okay. So that's kind of the basics of the platform. Are there any like urgent questions on that. And actually, what I'm going to do, and I'm going to tell all you guys to do before I take questions, is it takes a second to import Qiskit. So run this cell like now, and it'll take a second. You can see, or maybe just it ran much quicker this time. Maybe because I already imported it once. But the first time it was on the star over here for like 30 seconds to run it. That's one thing to note, is whether there's a number here or a little asterisk tells you whether or not whether the cell has been run. So if there's nothing, it has been run. If there's an asterisk, it's currently being run. And if it has a number, then it's been run at some point. I've gotten a question, Elon, about how you show the parameters of a function. I mean, I normally just like define them in my text. I don't know if there's like a way to print them like in Python. I don't know the way to do it. I'd recommend Stack Overflow. I'm sorry, I'm not a super Python expert. So I know enough in order to use Qiskit and to do everything I need to do in lab, but I'm definitely not a programmer at heart. Yeah, you can print the parameters of your function in that function, but there might be a shortcut that I don't know of. Okay. So yeah, definitely just like if there's any questions as we go through, if you have any issues, I can help debug. Then just post it as we're going through. So what we're doing here is we are importing a bunch of different things from Qiskit. We're importing their quantum circuit, I guess, library package. I don't remember what the term is for it. I guess package is what we call it a lot, or tool. We're importing execute, which allows you to execute these circuits. We're importing error, which is the backend that allows you to simulate them. Just to be clear, the circuit one is just to define the circuits. We have visualization, which does the visualization, and there's different things that we're importing. We want to be able to do histograms, a blocks representation, and then also a block multi-vector representation, which is meant for like multi-qubit things, but I don't totally understand how this guy works. Their documentation is not super clear on it. Oh, is it too small? Let me zoom in. Is that better? Hopefully. Cool. Cool. So with this, we just imported all of the Qiskit functionality we need. And we have more documentation on what all these things do. IBM does provide really, really good documentation for all of this. Overall, even I don't find this documentation clear, but like most of it is quite good. So you can use that if you are ever confused about anything. And there are one thing that we'd like to note, just especially if you're running this on your personal computer, if you're running it on Quantum Experience, it tends to be like updated regularly. But if you aren't sure if you're running it locally and you're not sure what version you're running, you can run this command, these 2 underscores Qiskit version, and it tells you what version you're running for each of the, I guess, Qiskit elements, they call it. It's very gimmicky, but they have like their Qiskit Tara, which is kind of like the base of everything, Air, which is a simulator, Aqua, which is more applications focused, and I think Ignis is like more optimization focused. But I only really use these two as far as like what I'm really like aware of. Or this Qiskit IBMQ provider is what you use to sync up with their backends for running on their actual hardware, and then this is just the overall Qiskit package version. Yeah, it's always good to just make sure you're up to date with everything. You can also just make sure to update all your packages on your local machine with pip or whatever if you're running that. Cool. So now that we have everything hopefully working and running, you can build your first quantum circuit using the Python interface. So the like it says here, the fundamental unit of Qiskit is a quantum circuit. So whenever you want to do pretty much anything, you want to initialize a quantum circuit object, which you can pass in different parameters to. So what we're going to be doing today is just defining number of qubits, in this case 1, and we're going to assign this object to this variable circ. It's funny because circ with a Q is Google's quantum like programming package. So we're going to use a C instead. And you can run this and it will just initialize a quantum circuit with a single qubit. There we go. And all the qubits will start out in the 0 state by default. You don't have to initialize them or anything. And you can also name this anything you like. I could name it circ with the Q for fun if I wanted to. But then we can also visualize the circuit that we've created to make sure we created what we expect, which you can do with quantum circuit.draw. So in this case, we already have created an object of a quantum circuit, which we called circ. So we just do circ.draw to draw the circuit we created. And this MPL here is short for matplotlib because we are using matplotlib for all the visualizations, I think, in this lab. In general, you can set which backend you use for your visualizations, but matplotlib is a very common choice. And you can see it's already run here, which I did just in case the servers got overwhelmed. But it'll just do the same thing. And you can see that there's just one line here, like a Q and then a single line. And that's just our qubit. We just initialized 1 qubit. You can change the number of qubits. So if I change this to 2, run this again, now I have 2 qubits and it now indexes them with little 0 and little 1. So you know which one you're operating on. And then also, if you remember from lecture, there's something else you can do. You can create bits that aren't qubits. Does anyone remember how you do that? Thank you, Mason. I'll see if, thank you, Austin and Jade. Yeah, you guys remember well. You can just add a second parameter. So I'll just add 2 classical bits too. So now we have our 2 qubits and our classical bits. It's kind of ugly how it printed. We can see that's trying to be a 2 there. And the classical bits are all on 1 line, but which is the exact same as the visualization and the graphical user interface we previously used. So this should all be very familiar with what you saw before. But what we're going to do for now is just switch this back to 1 single qubit, and you can of course change the number of qubits whenever you want to play around with this on your own time. Okay, so are there any questions on this? Gotten a note that you don't remember anything from lecture. Well, that's what lab's for. You don't have to remember anything from lecture because we go through hopefully the fun parts a second time. Okay. Cool. Next, we are going to go through adding gates to our circuit, and we're going to initialize a 2 qubit state to create Bell states. So the Bell states that we can create, of course, these are all entangled states that are maximally entangled, and they can be either the 0, 0 plus 1, 1, a 0, 0 minus 1, 1, or a 0, 1, 1, 0 of also like positive or negative phase. And this is the kind of standard notation, this phi and this psi to refer to these Bell states. So in this lab, we're just going to be creating this first state, and that's kind of like when people say we're creating a Bell state, typically they refer to this one, not for any particular reason, I guess, but all the rest of these are equivalently as good Bell states. I think this one's also kind of the simplest to, kind of the simplest to create because it's just a single Hadamard and then a C naught. And you need some kind of rotation, like phase rotation, to get some of these others. Cool. So with that, again, we have a lot of text. Don't like get too focused on reading through all of it. You can definitely read through all of it after lab, since you have all these all this documentation. But we're now going to go for our 2 qubit states. Since we now have 2 qubits, we now have 4 basis states: so 0, 0, 0, 1, 1, 0, and 1, 1. I guess actually I noted it. I'm going to fix the notation that I used on the slide. So I was slightly off from how I did it. But yeah, so this guy is your 0, 0 state. This is your 0, 1 state. This is your 1, 0 state, and this is your 1, 1 state. And this is just the amplitude of this, I guess, combined state. Like your qubits are no longer like independent entities. You can't just represent them on a block sphere by themselves. They are now like kind of like involved with each other. You have a 2 qubit state that you're dealing with rather than just a single qubit state. And so what we're going to do is initialize the 2 qubit state we want, and then we're going to we're going to initialize our 2 qubits and then perform rotations on them to initialize this Bell state that we want to work with. So like I said, the 2, and like we went through last week, the 2 operations we need are just a Hadamard gate and then a controlled NOT operation, or a C0 gate, or also a CX. There's a lot of different names for it. And don't worry if these, like we've gone through these gates a few times, but we'll be going through them much more formally in lecture in the upcoming weeks. So what we're going to do now, we're going to go through this hopefully like not too quickly, as we want to create a quantum circuit object that we're going to call circ_Bell, because we're trying to create a Bell state, and we're now going to operate on a register of 2 qubits instead of just 1. So the first step, after we've created this Bell state, is to add the Hadamard gate on qubit 0, which puts this qubit in superposition. And if you remember, actually, I could go and show you what this looks like. It's here. So we do actually have this exact circuit in the IBM quantum experience, which we made last week. So that's all we're doing here, is just doing that same thing in code. And so this first step of initializing the circuit, sorry, there's a bit of a lag, is just creating these 2 states when we set how many qubits and registers we wanted. That's all we're doing here. We did, of course, add classical bits to use for readout. But if we're not using readout, we don't actually need to have classical bits for anything. Or if we're not using any gates that require classical bits, I suppose. And then we added the Hadamard gate to our Q0. And that's exactly what this line of code here does. This is adding a Hadamard to our circuit that we've already created. Oh, sorry, I'm a little bit behind on the synchronization. We're adding a Hadamard to the circuit we already created, and we're doing that on qubit 0. And then the second step is to do the C0 gate, or the CX, which they call it in Qiskit. So this is the same thing. One thing that you'll see a lot is whenever you see something that's like a NOT, that just means an X rotation. And whenever you see a thing that says it's a phase, that means a Z rotation. And I guess it's just the more intuitive name for it, but people do use them interchangeably. And so now we're adding our C0 onto our 2 bits, where we have our control qubit 0 and our target qubit 1. And that's exactly what we have over here, where our control bit, this little like closed circle, is on qubit 0, and our little plus is on qubit 1. And these measurements we're not going to be doing because of what kind of emulation we're going to use. And I can go through what the differences are between our emulators if you want to know more about that. So back over here, we can run this and it will just output something that looks very, very similar actually to the visualization here. Oh, and I got a question about a quantum circuit being not defined. Yeah, so that's one thing. Make sure to run every single input in the notebook, even if it actually looks like it was already run. If you haven't run it on like once importing it, it won't actually have anything imported correctly. So definitely like make sure every single input has like little note beside it that it's been run like this 30. Oh, there's a bit of a lag. Yeah, there's a 30. Hopefully it's not too confusing. Okay, cool. So now that we have these circuits, we have this all initialized in our simulator, and we can now like measure the outputs that we get for this. But before that, we have a pop quiz. No one expected this, but yeah. So the first question is just in our circ underscore bell is equal to quantum circuit 2. What does the 2 represent? So we initialize it, and we just have a single input. So I'm getting a vast majority people are right on. Give you guys another like 30 seconds to fill it out. And of course, the answer, like the possible answers are the number of circuits, number of qubits, number of gates, or something else entirely, like none of these above. No one was scared of the pop quiz. Darn it. I mean, it doesn't matter at all. We're not recording like what you guys actually put in. It's just to see like whether it makes sense. So yeah, the vast majority of you guys were right on. That the 2 is the number of qubits. We only have one circuit, I guess. The circuit objects, the circ bell is our circuit object. It doesn't actually tell you the number of circuits you have, I guess, but it is a circuit initialization. You could, I guess, if you remember from your Python, you can make a list of quantum circuits and I guess print the size of that list, and that would be your number of circuits. So that is possible. But that's not what this 2 represents. The number of gates is something that you can kind of define as you go along. I don't know if there is, if they save the number of operations that have been implemented on a particular circuit. That might be something you can output, but I don't know how to do it off the top of my head. Obviously, we did do two gates on it, but that's not, it's not in the initialization. That's something that we kind of did one operation on it, and then we did another one. But the actual initialization was already defined before we ran either of these operations. Okay. Oh, you guys were scared of my pop quiz. Oh, I feel so powerful now. I don't want to frighten you guys, but yeah, no, that's fun. Okay, so now we have our second pop quiz. I'm gonna like try to go through so it's not as confusing. Second one is if we do circ underscore bell dot h and then this 0 in parentheses, what does this 0 represent? And the options are the number of gates, the qubit on which the Hadamard gate is applied, the outcome of the measurement of the state of the qubit, or the initial state of the qubit. So there's many options, or something else entirely. Maybe I've given you a bunch of fake answers, and I'm just trying to mislead you. Okay, and I'll give you guys another 30 seconds. And I see you guys are really struggling in the chat. I hope you guys are okay. Just make sure to click the right answer before you faint. That's all I ask. Okay, so looks like I got most of you guys have answered. yeah, and also the vast majority of you got it right on. The 0 in this case is the qubit on which the Hadamard gate is operating on. Again, the number of gates isn't specified on any given gate operation. You can always add more gates afterwards. The outcome of the measurement of the state of the qubit, you have to perform some kind of emulation or some kind of operation, like get that output. Also, if you were going to perform, like if you're performing a gate on a qubit, you probably don't want, like you don't specify your output. The gate will specify the output for a given input. You can think of it as, a lot of times we'll call it a black box, where we've given it something and it outputs something. How it does that, we don't really care, but we do know like what it will do with any given input. So outcome is always a bad bet, I guess, for some kind of operation, since we generally define operations with regard to their inputs. And the final option in the initial state of the qubit, it is, I guess, technically it is the initial state of the qubit. Were correct technically if you put that, because all the qubits are initialized into the 0 state. But where the 0 lies in this particular formula, it refers to the qubit that we're operating on, not the state, even though it is in the 0 state beforehand. Okay, so with that, we have our final pop quiz, or well, we have one more after this, but the final one for this little section. Thank you, Heath. So your final question for now, and then you guys can be less stressed. And in this, the 0 and the 1 refer to, I guess, what do they refer to? They refer to the control qubit and the target qubit in that order. So the 0 is the control qubit and the 1 is the target qubit. Is it reversed? Are these the possible values of measuring the qubit? Or is this the value of the qubit before and after the gate? Or is it something else entirely? Okay. Give you guys another 30 seconds to go through that. So I've gotten like 70% of you, 60% of you. And most of you guys got it right on. This is the control qubit. Qubit 0 is our control qubit. That's what the little dot means. And then qubit 1 is our target qubit, which is the qubit with the plus on it, or the not operation. I guess it's just convention which order it goes in. 0 and 1, you are correct, are the possible values of measuring a qubit, because those are our two computational or z-basis states. But that's not what they mean in this context. But they are, that is also a use case for those two numbers. And I guess the value of qubit 1 before and after the gate, if you input a 1 on the 0 state and you're talking about the 1 state, like you would get that. But again, we don't ever specify the output of a gate. Like we're never going to put in an input that somehow defines our output exactly, I guess. If you just have like a buffer operation or a identity operation, then it will be the same before and after. Or if your gate, like if you have a 0 input on a controlled gate, then yeah, the control will not do anything. But this is not like, you just in general, like do not expect that you'll ever be putting in something that defines the output of a gate. Okay, cool. So are there any questions on this section? Because we're now going to move on to simulation. not seeing anything, so I'll move right along. So now we can use our simulators in Qiskit to view the state of our circuit. So we haven't actually computed the output of our circuit yet. And what we're going to be using is, like I said, Qiskit Air, which is all these different backends. And we can use many different simulators of this. So there's the Chasm simulator, which is the, like, I guess, artificial simulator that we used with the quantum experience last week. We can also use the state vector simulator, which pretty much just multiplies the results. I guess, like, it's ideal. It's not going to give you any errors, and it just executes it once. So you're not going to have any noise. You're not going to have any deviation from the expected behavior. And then you also have the unitary simulator, which I think the only difference is that it returns the unitary matrix at the end of the circuit. Like, so, like, whatever your circuit did, it'll return the entire unitary of your entire circuit. So, like, it can multiply all the matrices together. Well, this guy just does the final state vector. And so this one specifically cannot handle any measure or reset operations. You also don't need measure or reset operations for the state vector simulator. And that's why we don't need to add any classical bits, because it will just multiply through our matrices for the state vector simulator, while the Chasm simulator does try to emulate the Hamiltonian of our actual quantum computer. And so you do need to have these classical bits to measure, and we have to perform a measurement operation, and we'll get some deviation from ideal behavior. Okay, got a question from Clark just before we get moving on running the measurements. Wouldn't the qubit outcome change from 0 to 1 to plus minus if you measured along the x-axis instead of the z-axis? So if you could perform a measurement on the x-axis, you would be getting outputs from your plus state and your minus state, but physically we can only measure observables of our system. And so energy is an observable, but energy is along the z-axis. There aren't any observables that are along x and y that I think we can implement, at least, or some that I know of. But what, like I kind of drew out with the circuit, we can perform rotations on our qubit state before we perform the measurement. So we could perform a Hadamard gate on our qubit state, and that will rotate something that's on the equator, so in the plus minus basis, up to 0 or 1, and that will allow us to measure it and, like, do a x basis measurement with a z basis physical measurement. So even then, our actual physical output would be a 0 or a 1, but we don't have to treat it as though we're just measuring that. Like, what we're actually interested in is the value of the value of our state on the equator. Okay, we also got a question from Elon about how so far all these circuits are very easy to simulate on a classical computer. Where does it get difficult to simulate, and why? So I don't know if we already went past the part where I noted this, but if you just add many more qubits and you need to initialize all of these qubits on your computer, because it scales exponentially, you will very quickly reach a point where your computer will not be so happy trying to simulate it. But if you're only implementing like a single qubit behavior, I guess, where you have to encode your phase and your 0 or 1 state, then you will have like, that is like a decent amount of information. It's not just like a single classical bit, but generally, like, you do need on the order of like 64 qubits is what people normally say, to show like a clear quantum advantage or quantum supremacy. But there's also a lot of tricks you can play if it's for a specific problem that makes it harder to show a clear advantage, even if you have so many qubits. The real difficult point in a like quantum computation is often the time evolution of the system, where to store all of the parameters, like to store the phase of your qubit and store how it evolves in time at every single point, along with, and when you have many different qubits that are in some superposition or some entangled state, then that is when you start to get issues with running these simulations. If you had, I don't know how many entangled qubits you'd need for this kind of simulation where it would become a problem. But you could try running it on either, I guess, like you could run it on the quantum experience and see at what point it just never finishes running. And that'd be a fun little test. Just increase the number of qubits repeatedly until you get there. I don't think it would be too many, but I couldn't tell you exactly how many. And of course, if you're doing something like this, like state vector or unitary simulator, this is just multiplying through the matrices. So that will be quite a bit quicker than the QASM simulator, where it's trying to emulate the actual behavior of a real like physical quantum system. So it's a bit different. This guy, I guess, like this wouldn't actually inform you whether it'd be hard to solve a particular problem, because what this is trying to do is it's trying to tell you like how similar, or like how your circuit would actually behave on a real quantum computer, where these are just performing the mathematics. But there are cases in which I guess directly doing all the math would take a very long time, and you need to have some kind of approximation to perform those mathematics. So hopefully that was not too rambling, but it is a very complicated question. Google even has struggled quite a bit at finding a really good test to show quantum supremacy. And even their paper that like claims quantum supremacy, a lot of things, like it showed all it showed was that its computer was very good. It didn't manage to show like a particular problem that people are interested in that they can solve that other people can't. Okay, cool. So now what we're going to do is take the back end for our Qiskit, for our Qiskit Air simulator. And in this case, we're going to be using the state vector simulator, like we said, which will just return our quantum state. And so now all we have to do is just execute our circuit. So at the point where over here, wait for it to load, we ran it on our quantum simulator, or we didn't even have to run it for the state vector simulator. We just did this and it just automatically propagated. All we're doing now is we're going to execute this job with our circuit passed in here and our backend passed in here. And we have I'll run that. It doesn't take very long, but we have our final poll question for the day, which is more of a programming question. And it's which are the output or the inputs to the execute function. So when we run this, I guess we only have the option to put in, like, if there can be multiple that are correct. So put in one that you think is correct, or put in whatever you feel is the best. It's, yeah, I know it will only let you select one. I don't know how to make it select more than one. That, yeah. And I'll give you guys another 30 seconds to think on that. Okay. Cool. I've gotten again like 60% of you. Yeah, and I think vast majority we get, I mean, I feel like I would give 3 correct answers to this. The correct answers are circ_bell and backend. These are the 2 inputs that we're passing into the function. So if you put B, C, or D, I guess I'll accept any of them. Yeah, because technically, like, yeah, there are 2 inputs, not just one or the other. But yeah, I believe there may be more like non-required options to this function. You can look at the documentation if you have any other things you're interested in maybe modifying for the behavior. And then the last bit is whenever you've run a program or yeah, I guess call it, like, whenever you execute your quantum program and you assign it to a variable, this will just have your job as it runs. So if you're running on a physical quantum computer and you're waiting for a long time for your job to be at the front of the queue, then you might want to check on its status. So you can use job.status, which is just a function with no parameters, and then job.result, which will return the result of your job. So because we just ran this with a state vector simulator on our kind of cloud, rather than going to one of their physical quantum computing backends, we can just grab the result immediately, and that's going to be stored in our results value. And then we can use the method get state vector from our circuit that will allow us to get like our state vector out, and then we can print it. And you can see, sorry, we print it here, but we can run it again. And this just has, this is square root of 2 plus no imaginary part, and then like net like 0 in the second part. It's very hard to read. There's not really a great way to print this out. So this is what you expect to get. And then you have your 0 imaginary part, or 0 value, I guess, in general, and then your square root 2 plus 0 imaginary part here. And this is just a square root 2 for each of our like populated states, which is our 0, 0 and our 1, 1 state, and the 2 in the middle are equal to 0. Yeah, so it's a bit hard to read, but this is the value we do expect. And once you have this results object, you could kind of emulate the behavior that you would get if the circuit was run many, many times. And you can do this by get counts. And so this will just like pretend like it's run the circuit many times and give you the actual output of it. And you can see here, it's giving you a 50-50 shot of each. And then you can print your, plot your histogram for this, and you can see that it's just the 0, 0 and the 1, 1 state. And so that's actually the exact same. Let me bring this guy open. I mean, it's not quite the exact same, but this is actually, I ran this on a physical computer. Let me get the simulated version. So it looks a little bit more similar at least. You can see it's very close to 50-50 when it's run on a physical quantum computer, but there is some deviation because it's not a physical quantum computer, but it's run in emulation as if it was on a physical quantum computer. You can see there is some deviation just due to the finite number of iterations we run. This would converge to 50-50 if we ran it an infinite number of times. Okay, so that is, I guess I kind of answered the discussion question a bit myself, but do you guys notice anything else on it, I guess, or do you have any thoughts on these histograms? Does it make sense why they are different from the versions that we created with the quantum experience last week? I'm not getting any questions. So I guess with that, We have some key takeaways at the bottom and further reading available to you guys. And I'm actually on time, which is very rare. I'm gonna stop sharing. And I guess we can do the post-lab Zoom feedback, and I can take any more questions if you guys, if you guys have any. You can go to my iPad to annotate if you have anything that needs writing out. Okay. Okay, I've gotten a question from Tomas. If to use a real quantum computer, will you use the same kind of code? Yes, you'll use exactly the same Python code, and you can run it on a different backend that's like a physical IBM quantum computer. If you, like for me, like since I have quantum computers in lab that I can run on, we have our own interface that we use for them, because we do have to control the pulse sequences and kind of the physical implementation. But it's always kind of the same principle, and we do actually code it in Python as well. But yeah, as far as quantum computers that you can access online, the IBM one just uses Qiskit. Cool. I've gotten another question from Jonathan. If energy can be transferred outside of a quantum computer and entangle it like with other things? That's actually a very good question. That's a big open area of research, I guess, is the idea of an open quantum system. And all of our quantum computers today are open quantum systems. We can't perfectly isolate things from the environment ever. So we do have to, in some way, model like the noise, the dissipation, whatever from the rest of your environment. Trying to like entangle it with, so the funny thing you mentioned, entangling it with energies from your brain is a very interesting point, because that's actually something that people do use quantum sensors for. You can use nanodiamonds, which are just like small chips of diamond that house defect centers. Like we've called them NVs, or we've called them defect centers before. And they're just nitrogen vacancy defects, where a nitrogen atom has pushed a carbon atom out of the diamond lattice and replaced it with itself. And then it has another vacancy adjacent to it that's just a hole in the carbon lattice. And these sensors can be optically addressed, and since they're made of carbon, they're biologically very neutral. And so people are very interested in using them to sense different biological things. I don't think they've actually been approved for human use. I don't know if they have any human testing on it. But so the thing is with nanodiamonds and like any kind of nanoparticles is that they're so small that they're really, really bad for you. Like if you inhale them, like they're like absolutely awful for your lungs, because they're just too small and they can permeate through things that they shouldn't be able to permeate through. So they are still dangerous from like a particle perspective, even though the material is totally safe. But that is something that people are interested in I guess, sensing tiny magnetic fields from your brain using that. It's not really entangling a coherent quantum state, because if you're looking at like a biological process or a complex environmental process, it's not in a pure quantum state, it's in a mixed state of many, many different quantum states. So it's hard to get useful information out of that, but it does have a well-defined magnetic field in a lot of cases, and you can sense the electrical impulses in your brain or moving through your body. And so what they do is the magnetic field causes a shift in your quantum states, like that's proportional to the field. It's called the Zeeman effect. And then you can measure how much that shift is. And so that's what they use these sensors for. But yeah, very good question. Okay, so I think that's the last question for today. We are only 5 past, and I think this went very well timing wise. I hope you guys learned a lot, and I hope you managed to make some new circuits just playing around with Qiskit or the quantum experience this week. It's very hard to break, so try whatever whatever inspires you. And if you feel like you've broken something, you can just open up a new notebook and you can't hurt your computer because it's on IBM's cloud servers. And so if you hurt anything, it would be their cloud, and they won't let you do that. So yeah, hope everyone has a great week. Yeah, if you manage to break IBM's cloud servers, I will be very, very impressed. And I think IBM will be very, very impressed too. Yeah, okay, bye everyone. I hope you have a great week, and I hope you break IBM's cloud servers. Don't tell them I said that.